Hey everyone, this is Aurora with Supercharged Science, and today we're going to do a hands-on science class in the science of heat and energy and basically physics. So if you like this and you want more, go to my website and get some more free stuff like this. You want to go to www.superchargedscience.com/free stuff, or you could just go to superchargedscience.com and click on the button that says free stuff, and you just put your email in and then you'll get free science experiments delivered right to your email box. Okay, so we are going to take a look at the science of heat, thermal energy, thermodynamics. So if you've got kids that want to learn how to make it rain indoors, they want to boil room temperature water, they want to figure out what the triple point is all about, and you want to get your kids to take a bath on command, this is the right class for you. So we're going to spend about 15 to 20 minutes together. So let me do that right now. Okay, ready? Question number one. Imagine you've got a ice cold glass of water just sitting there in front of you. You see it? It's got the ice cubes, it's got the water, it's just chilling. Wait a minute, are those water drops on the outside of the glass? Have you ever seen what would happen? Have you ever seen that happen on an ice cold glass of water? Like where did the water come from that's on the outside? And why is it sticking to the outside of the glass? What do you think? Did the water somehow leak through the glass? Did somebody come by and squirt it with water? What do you think? No, of course not, right? Okay, here's a deep breath. All right, here's what's going on. Take a deep breath, let it out. What did you just breathe in? Air, right? Okay, so what's air made out of? If you could look at it under a really powerful microscope, what would you see? You'd see water molecules in addition to the nitrogen and the oxygen that are there. Water molecules, huh? Okay, so little teeny bits of water that you can't normally see. So those little bits called molecules, they make up absolutely everything. So basically they're through the water, and when you put certain, those molecules hit the ice cold water, it goes from regular 70 degrees to something closer to around 30 degrees, and it'll instantly bring that water out of gaseous form and turn it into a liquid. So imagine if you lived several hundred years ago and condensation wasn't yet discovered or wasn't understood the way we know it as today. Can you imagine if you just saw this happen and you'd be thinking, wait, what just happened? You'd be pretty amazed, wouldn't you? Even though this happens all the time, most people don't actually notice it. You have to be a really curious person to understand to even notice things around you, and that's what makes a really great scientist. Here's something else most people don't even think about, but if you're curious, this will make your head might go, what's going on here? Okay, here it is. Okay, let's play a game called Hot and Cold. Imagine a desk, the kind you'd find in a typical classroom. You know the kind, I mean, the wood desk is attached on the chair, like you see here in the slide. Okay, which one is colder, the wood table or the metal legs? Quick, tell me, if you touch it, which one's colder? Yeah, the metal, right? Okay, which one is colder, the metal screws or the plastic seat? The metal screws that go through here. Yeah, the metal screws feel colder, right? Actually, the answer to all of that is they're all the same temperature. What? Let's take a look at this again. Take a look at it. This chair has been sitting in the same room, right? You just didn't pull the metal legs out of a freezer and stick the wood desk that was part of an oven, and then stick the whole thing together. No, they've all been sitting there in the same classroom with the same temperature, with the same air circulating around it. So there's nothing that makes the legs a different temperature than the wood, right? Okay, so the question is, well, wait, why does it feel colder? Why does metal feel colder than the wood or the plastic when they're all the same temperature? What do you think? Tell me out loud. What do you think is going on here? Okay, so the metal is going to feel colder because heat flows away from your skin faster into the metal than it does the wood. Now this is called heat capacity. We'll talk more about that in just a minute, but this is why scientists had to invent the thermometer, because the human body, it's not really designed to detect temperature. The human body can only detect what we call heat flow. So these are two totally different things. Heat flow is very different from temperature. Okay, now notice that I said that the wood and the metal parts are at the same temperature, even though they don't feel like it to your body. So the question is, what's temperature? Temperature is a way of talking about and measuring and comparing the thermal energy of objects. Now, there are three different kinds of scales that we have today to measure temperature. Technically, there's four. There's the Fahrenheit scale, there's Celsius, and there's Kelvin. Notice Kelvin is the absolute scale for Celsius. You don't have like -3 Kelvin. It would just be, it goes from 0 on upwards. You can go from Celsius to Kelvin just by adding 273. So 0 degrees Celsius is 273.15 Kelvin. Okay, notice I didn't say degrees Kelvin. It's just Kelvin. Okay, now to get from Fahrenheit and Celsius, you've got to do this little complicated equation with fractions, and now you know when it's something is 0 degrees Celsius, it's 32 degrees Fahrenheit. Okay, there's a fourth scale called the Rankine scale, which is the absolute scale for Fahrenheit, and you'll learn about that if you're an engineering major in college. You have to add about 460 to the Fahrenheit number here in order to get what it would be in the absolute Fahrenheit scale. Okay. So with so many temperature scales, you can see how scientists have to be really careful about which one they're using in which equations so they don't get mixed up. Do you see all these numbers here? These are all from the same thermometer. So that thermometer can read 32 degrees Fahrenheit, 0 degrees Celsius, 273 Kelvin, or 492 degrees Rankine. So you can plug all these numbers in and it's all the same temperature. They're just different scales. So if you're using an equation that has temperature, for example, to the 4th power in one of the heat transfer laws, so heat transfer equations for radiation, so 500 squared is very different from 32 squared or 0 squared. Do you see how it'd be really easy to make a mistake? That's why you've got to be really clear as to which value you're using. Like 1 mile is very different from 1 kilometer, which is very different from 1 centimeter, right? And in that case, they're measuring different things. But in this case, they're all the same. You just got to make sure your scale is right. Okay, so why are there so many different scales? Basically, what happened is Mr. Fahrenheit, back in the 18th century, he was puttering around in his lab and he created a scale using a mercury thermometer, and he marked the 0 spot when he measured the temperature of that ice melts in a tub filled with salt. And that's why ice actually melts at a lower temperature when it sits in salt. That's why we salt our driveways, to get rid of the ice. To find the higher part, he looked around and he found his wife. And he said, oh, I'm going to measure your temperature. And he found it to be 96. So over time, his scale was made more precise today. So body temperature is usually 98.6 degrees. And later in that same century, Mr. Celsius came along and he created his scale. He decided to use water as his standard, and he chose the temperature that water froze at for his 0 mark, and then he chose the temperature that water boils at for his 100-degree mark, and from there he put 100 evenly spaced lines, and that's the Celsius scale. Then Mr. Kelvin came along, and he came along and he wanted to create yet another scale. He said, I want my 0 to be 0, as in nothing moves. There is no energy, no thermal energy in there at all. Never anything less. So he chose absolute 0 to be the 0 on his scale. Okay, so what we have is we have one guy who said, okay, I think 0 degrees Fahrenheit is when water freezes with salt. And another guy said, I think 0 is when water freezes. And one guy said, oh yeah, 0 is when atoms stop. So you have all these different people with different ideas and scales, and it gets all mixed up. Okay, let me tell you enough about that. Let's take a look at, now that we know how temperature is measured, what is temperature actually measuring? It's measuring the amount of thermal energy, which is how fast the molecules are moving in something that is vibrating and moving. So the higher the temperature, something that has a higher temperature, that means the molecules are moving faster and more. So water at 34 degrees Fahrenheit has molecules moving much more slowly than water at 150 degrees Fahrenheit. So you can think of temperature as really like a molecular speedometer. So when something feels hot, the molecules in that something, they're moving really fast. And when something feels cool, they're moving not quite so fast. Now you can't actually see these molecules, which is why it makes it a little funny. But your body has different antennae to detect this type of energy. Do you know what it is? So your eyes can detect certain frequencies of light, right? And your ears can detect certain frequencies of sound. Your skin, your mouth, your tongue, your fingers, they can all detect energy, thermal energy, as hot and cold. So there's a really cool experiment I want you to do. Now just pay attention at first, and then I'm going to walk you step by step through it, and then we're going to talk more about triple point, and then you can go back and do this after we're done. Okay, ready? So here's an experiment you can do at home. So First, you want to get 3 cups, and I colored mine so you could see that they were different, but you don't have to color yours. So hot water, now I mean hot like 130 or below, not something you're actually going to get burned with. So hot water, like hot enough you're like, yeah, that's hot, but I can still leave my finger in it hot. Cold as you can get it, like ice water. And then this is just regular room temperature water. So here's the idea. You're going to put 1 finger in each one, the hot and the cold. And then while you're doing this, you're going to sing your ABCs twice at regular speed. Okay, so basically about a minute-ish, you're going to keep your fingers in. And then what you're going to do is right as soon as you're done, you're going to take both fingers out and put both of them into the warm water. And you're going to see what you can detect. Okay? Now remember, the sensors in your finger, they will detect body change temperature. So it's going to detect the change. So you can imagine if you heat one finger up and you cool one down and then you bring it to a warm one, what do you think is going to happen? All right, I'll give you a few minutes to actually try that one. I'm actually going to talk to you really quick about another part of thermal energy. So there are 3 states of matter, right? We got solids, liquids, and gases, right? Actually, there's 5, and actually, technically, if you're a chemist, there's 18 states of matter, but for most people, 3 to 5 is just fine. Water is really special because it can be a solid, a liquid, or a gas state at pretty normal temperatures. So you don't have to be like, have a mad scientist lab in order to make it to go into any of these states. Helium, for example, is not like that at all. It's very unfriendly, but we can make it go into a liquid. Okay, so if you take a look at the water here in these 3 states, we've got water in the teapot and it's boiling, right? And we have steam coming out, that's water vapor. And this is an ice waterfall. This is a waterfall that's frozen. So water in its solid state, basically when it's an icicle, right? It's holding its shape. The water in there is, the bonds between the molecules are very strong and stiff, right? Because you can see it. The matrix that holds the water molecules in it have a crystalline pattern. They form ice crystals, right? Okay. So if we break off one of these crystals and stick it in the teapot and heat it up, those bonds are going to loosen up and allow the water to go from a rock hard solid state to kind of a loosey-goosey, kind of a liquid sloshy state. And if we heat it up even more, add more and more energy, more and more thermal energy, it's going to come out and they're going to be zooming all over the place now. Now this has the highest amount of energy in there. Okay. So one more thing I want to talk about is heat. You know, we've been talking about temperature, and temperature is not the same as heat. And believe it or not, the concept of heat is actually really tricky. We call it heat in the common language. What we think of as heat is not really heat when you're actually a physicist. So heat in a way doesn't really exist. Nothing has heat. Things can have temperature. I have a temperature of 98.6, right? Things can have thermal energy, but they can't have heat. Heat is really the transfer of thermal energy, or in other words, the movement of thermal energy from one object to another. So if you put, here's a slide, if you put an ice cube in a glass of lemonade, what's going to happen to the ice cube? It melts, right? Okay. Which way does the heat flow? Okay, so the thermal energy goes from the lemonade, it moves into the ice cube, right? Because heat goes from hot to cold. I can't tell you how many times in my heat transfer classes in mechanical engineering, students would say heat actually goes from cold to hot. Obviously, they've never had a cup of coffee on a cold morning, chill down and just be a cold cup of coffee. So heat goes from hot to cold. That's a standard law of thermodynamics. So coffee cools down on a cold morning, and lemonade heats up, right? So that's one of the things that you want to get from today. So you'd be amazed by how many people just don't know this. They'll turn in their homework assignments and final exams with arrows pointing the wrong way, showing that heat flows from the ice cube to the lemonade, but actually the heat doesn't flow from the ice cube because it's colder. It has to flow to the ice cube. Okay, so here is something I want to show you. One more thing. Actually, let's do 2 more things. Okay, so we're going to talk about triple point, and then we're going to talk about how you can boil room temperature water, and then I'm going to leave it at that because I know this is kind of a thick class. There's like a lot of concepts in here. Now, by the way, if you've just joined us, my name's Aurora with Supercharged Science. We are doing a class in thermodynamics, thermal energy, and heat. If you like this and you want more, and you actually want more of this particular topic, you want to go to www.superchargedscience.com/easy. Like, wow, that was so easy. My kids are learning this stuff and I don't even have to know it. Easy. superchargedscience.com/easy, and you can sign up there for a trial of my online e-science program. And this is a small little tidbit taken from Unit 13 on thermodynamics, which is a huge unit. You spend like a whole month just on this stuff. You actually make fire water balloons. I'll show you how to boil room temperature water. You make little putt-putt steamboats that work in the bathtub. So now your kids are going to jump into the bathtub because they love to watch their little boats. You make steam engines. You make all kinds of things. So as you're studying thermodynamics. Okay, so I promised to teach you about the triple point. Okay, so did you know that you can have liquid water and solid ice existing happily together without the ice melting or without the liquid cooling down, and both are at the same exact temperature? Let me show you what I mean. Do you see this chart? This is what we call a phase diagram. Phase, like solid, liquid, gas, phases, okay? But this is for water, and every substance has their own different looking phase diagram. Okay. And so this is going to show you what state water is depending on its temperature, T, or its pressure, P. Let me show you how to read this before you get too scared. Okay, so first let's find a low pressure, okay, like the pressure maybe you're feeling right now. It's called 1 atmosphere, okay? So we're going to put our finger on the 1 mark on the vertical side right here. You see it? 1 atmosphere, okay? So that's what we're experiencing right now. And now we're going to follow this dashed line. So this is 1 atmosphere, and this is cold like Alaska. This is temperature that's below 0 degrees. This is below freezing, right? So we're in Canada, we're in Alaska, we're in Michigan, okay? And it's cold. And water in its normal state is going to be ice, okay? Now as we start to warm up, as we hit the freezing point for water, as it goes across, we hit 0. Now we turn into a liquid, and if we keep going up to 100 degrees, keep going, keep the pressure constant, so we're liquid, 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 and then we're going to heat this, and this is the teapot on the stove, and now it's in a water vapor phase, okay? Phase and state mean the same thing here, solid, liquid, gas. These are 3 phases, 3 states of matter. Okay, so now let's find the 0 on the temperature scale, not this 0.01, don't worry about that, but the 0 on the temperature scale. Okay, now we're going to hold temperature constant. Okay, so start at the bottom. You see at very low pressures, water is actually going to be a vapor, even though it's at 0 degrees. Isn't that wild? Now let's increase the pressure, increase the pressure, increase the pressure. So we're going to push on that water vapor more, push, push, push. It will suddenly turn from a water into an ice. It doesn't go through a liquid phase. This is a lot like dry ice. You've seen dry ice when carbon dioxide, solid carbon dioxide, it'll go from an ice. And when you heat it up, it'll sublimate into into water vapor. I'm sorry, into CO2 vapor, right? Okay, so same thing here, only we're going backwards. So now we're in water vapor, and then it'll condense straight into a solid chunk, okay? So now let's take a look at the line that separates liquid water from the ice. You see this here? Okay, so for water at 1 atmosphere, right here, this point here is at 0 degrees. So that's when it goes from an ice into a liquid, right? Okay, so if you have water that's right at 0, it could be ice or liquid or both at the same time right at 0 degrees. Now you might have seen this before in the fridge, right? If you stick a glass of water and you stick it in a fridge that's right at 32 degrees Fahrenheit or 0 degrees Celsius, the ice doesn't melt, but the water doesn't freeze, and you can have both in there and they'll happily coexist. Triple point is where you do it for all 3. Okay, so we have a pressure and a temperature that you can put the water at, where you can have ice, gas bubbles, and liquid water all happening at the same time. Now you have to lower the atmosphere quite a bit. You have to lower the pressure quite a bit, and it's just a little bit more than freezing here in order to get the triple point of water. Now, the triple point is actually, it's very useful. The place we found it naturally is actually on Mars. We found the triple point for carbon dioxide. Now, it's used for space missions. They can use it to calibrate their instruments. It's used on space missions to define what sea level is for their instruments on board. They calibrate like how they measure gravity, so they can calculate elevation of mountains. Oh, and if you're looking at this critical point, don't worry about that. It's just a spot where no boundaries exist. It's just one phase. It's like a supercritical fluid. You can't tell the difference between the 2 states because everything is just so crazy up here. That's not generally how we think about things. Okay, so to give you a quick visual on pressure, temperature, and volume, because we were just talking about that here. We were talking about pressure and temperature. You can think about this. Imagine a room full of ping pong balls that bounce around all by themselves, and they go zipping all over the place on their own. Now, if you take those ping pong balls and you add more energy, more heat to the system, what happens to the ping pong balls? Yeah, they zoom around even faster, right? Okay, now what happens if we take away energy? We stick this thing in the freezer. Yeah, it will take energy away. Will they bounce faster or slower? Slower, right? Okay, so now get them bouncing on their regular speed. Bing, 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 bing. Okay, now make the room smaller. You see that? Here's a bigger room and a smaller room. Okay, so we're making the room smaller. We're decreasing the volume, right? Volume's bigger, now volume's smaller. What happens? Are they bouncing more or less? They're bouncing more, right? Ding, 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 ding. They speed up. That's right. Okay, so the ping pong balls are molecules, and when you add energy, you're increasing the temperature, so they move around faster. When you increase the temperature, the molecules zip around faster and faster and faster. Now, if we have this volume and we go from a small to a big volume, they start to slow down. So increasing the volume on a gas will decrease the temperature, the ping, 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 the motion of the actual molecules. Does that make sense? Okay. So the pressure is how many hits or how many pings that the sides here and the top and the bottom feel. So if you can imagine here, when it was at normal speed, you know, it's getting hit, say, 10 times a second. But if you add energy and they're zooming faster, are there more or less hits per second? Yeah, there's more, right? So we increase the pressure as well. And if we decrease the volume, if we squish it down, now there's even more hits, right? So we increase the pressure as well. And this holds for gas, for ideal gases, which is gases like air, for example. Okay, how are we doing? You guys good? All right, last little trick. So you've already got the finger trick you're going to do. And I'm going to teach you how to boil room temperature water. You ready? This is super simple. This is the last thing we're going to do. And by the way, if you like this and you want more, you can definitely go to superchargedscience.com and sign up for some more free stuff. Okay, for boiling room temperature water, you're going to need a syringe with no needle on the end. Now, I got mine at the farm supply store in my town, but you can probably get them from doctor's offices. Just make sure there's no needle on the end because you're going to put your finger on the end. And here's what you want to do. So the first thing you want to do is look at the slide. Okay, so you're going to fill the syringe partway with water, and then you're going to put your finger on the end, and then you're going to pull the plunger back quickly and release, and do it several times, and you'll start to see gas bubbles appear. Now, the gas bubbles are actually the water that is turning from a liquid into a gas phase. Those are actually bubbles made out of water vapor. Pretty cool, huh? So when you originally fill this up, make sure there's no bubbles at all. And so when you fill it up, you're going to push it out a little bit to push out all the gases, just to make sure this is solid liquid, so you're not actually getting any air bubbles in there. Okay. So this is something you're going to need to practice with, because the harder you're pushing, so you're pulling it back, so you're decreasing the pressure. Remember, we talked about this. We're decreasing the pressure, and we're keeping the temperature the same on room temperature water. And so what we're trying to do is we are trying to decrease the pressure enough on, let's say you're about here. We're trying to decrease the pressure enough so it crosses this line and makes little water vapor bubbles appear. And so that's a super simple experiment you can do. Now, you're not going to get a ton of bubbles, but you should see a bunch of tiny bubbles, and if you flick the end of it and kind of tap the end, all the bubbles will coalesce together into this one bigger one. So when you have lower pressure, those trapped air bubbles will come out that are already inside the water. Pretty cool, huh? And so those little tiny bubbles inside, that liquid is boiling because it's changing state. Boiling has nothing, it doesn't mean it's boiling temperature, it just means it's changing state. Okay, so what do you think if you tried, instead of water, what if you tried like, soda? So that is some homework for you to try out. Okay, I know we went a little bit longer than I expected to, but I hope this has been helpful on your journey to becoming an amazing physicist. So if you like this and you want more, go visit me at www.superchargedscience.com. Feel free to download any of my guidebooks, sign up for free stuff. We have live free classes all the time. If you want to join my science family and join my online K-12 program, you can do that as well. Oh, you know, I had some people requesting to see the program before. Let me do that real quick. Okay, so if you'd like to join my science family, this is what it looks like. So this is the Supercharged Science website, and it's not very big. This is actually the old website, which is actually going to be taken down in about probably by next month. And here is the new website. And so this is our online science program, and you can go through it by topic, you can go through it by grade level. And so we have topics in energy, motion, matter, sound, astrophysics. Kids are actually making their own telescopes here. Light, electricity, magnetism, and they're making their own robots here. Thermodynamics, this is the one we just did today. We have electronics, 3 levels of chemistry, 4 different levels of biology and life science, and we have advanced AP physics, chemistry, and biology. And we also have a math course. So we have a ton. This doesn't look like much, but this is enough for 12 years of science. So you can go through it by grade. You can go through it by topic level. So if you have a student who's in 2nd grade, but they've done a ton of, say they're interested in electricity and they've already done a lot already, you can simply go to the topics area and you'll get all of the electricity content. It's not filtered out by grade. But if you've got a student who maybe hasn't done a lot so far, I would recommend by grade level to make sure you don't miss anything. Let me show you. So you can click, say, 4th grade. Suppose you got a 4th grader. And then you'll be taken to a page where these are the topics that you'll complete by 4th grade. So you can pick any one that you want. Okay, suppose you want to do, say you want to do electricity. And then you'll just click on electricity. And it has the science concepts that this area covers. And by the end, your student should be able to do this. And then here are the lessons. Oh, well, there's a button for your materials. And I should say the materials are standard everyday materials. And so you shouldn't have to spend a fortune to do real science. And you don't have to get exactly the same materials I do. I just do as a demo. Let me show you what I mean. So when you're on the site, suppose you're doing 4th grade electricity and you're starting out, you're going to select the first lesson. This has all the main ideas and the foundation. And we also include robotics in there as well. And then these are all the lessons. And so when you're ready to do one, you just click on it. And the lesson will come up. Am I logged in? I am logged in. Okay, great. And so this is where you are in the sequence. And these are all the different experiments you can do. These are all hands-on lessons. And for this experiment, you're going to need hair, a balloon, a yardstick, and a spoon. And you play it. Here, turn down the volume. You play it, and it shows you step by step what we're doing and how to do the experiment and how to set it up. There's also worksheets you can download and open up and put over here so you can see it. And with lab sheets, and there's extra reading, and there's exercises with answers. And so you can do all of these things all together. And if you have a question, you can write it in the comment box, and then you will be, and then you can ask a question at any time. So you don't have to worry about answering questions you don't really know the answer to. So that's available as well. And so this is how you would work through the program. And then when you're done for the day or done for the section, you'll go back to the main area. Oops, I went back too far. And then there's assessments that you can download to see how much your student has learned by the end of doing all of these labs. And we can open that up, put it back over here. And so each grade level for each subject has assessments. And we have quizzes, we have lab practicals, which is it's where you give the students a question and a box of materials, and they have to design an experiment in order to answer that question. And it really shows what they've picked up in that area. So we call those lab practicals. There's homework assignments and so forth in here, and you can download that. That's all available. And so the idea is that you would download those and stick it in a 3-ring binder. And so with your experiments, as you go through them, you're going to download the worksheets for the ones that you have to do. Now there's over, I don't even remember how many now. There's thousands of experiments on here. You don't have to do them all. So you'll be making your own science journal just based on what you decide you want to complete. And there's a lot of overlap here. So if you skip one, don't worry. You're going to get the concept in a different one. Okay? So you can go through the program there by grade level. If you have a high schooler, then you'll definitely want to check out the high school area. We have physics, chemistry, astronomy, biology, electronics, and energy. So in physics alone, there's 550 videos that show you step by step how to go through a full year's worth of physics. And there's chemistry, and there's a ton in here. And so that's just a quick little what you get. And what's really cool about this program is it's interactive. So as kids work through it, they're asking us questions and we're responding back. And so this program was made by myself and my team of scientists and engineers. Actually, I just had a neurophysicist design a whole section that we're about to post onto there as well, because honestly, I don't know that much about neuroscience, but we thought it was important enough to stick on here. We also had a PhD in chemistry who was amazing with kids, and she helped me with some of the chemistry videos. We have 150 new ones coming out next month, and so those are coming on as well. This is different than the DVDs we offer on my website. DVDs are more for people that don't have internet access and just want like a single topic that they want to go through. The eScience program is huge. It's much more comprehensive. We're constantly adding to it. And it's also, there's a lot of crossover. So you may be doing an experiment in say in electricity, but chemistry might be involved when you're starting to make your batteries, for example. So there's a lot of overlap. You're not just doing just motion or just mechanics or just chemistry. You're actually able to pick and choose and see how they really interact with each other. Speaking of which, a lot of the content on the website is actually given based on feedback. In fact, a parent about a year and a half, maybe 2 years ago, wrote in and said, "Hey, I really want my fourth grader to learn marine biology. But the only thing I found was this 12th grade textbook just in marine biology from a major publisher." And then that was it. But it was so thick and dense. I mean, no fourth grader is going to be inspired into going into study marine biology by studying this book. So I thought, what a great idea. And so I created an entire marine biology course, and I created an entire civil engineering course. So a lot of the career. So imagine you've got a kid who's interested in science. It's like, well, what career do I give them? So something I've put on the website now is careers in science. And so we have a bunch of these and we're adding to them all the time. And so what's really cool here is you'll find, if you're interested in chemistry, this is the kind of career you can expect. We have it for light, lasers, and holograms, robotics, renewable and alternative energy, solar astronomy, this one I think is geology, biology, and so much more. So it's not just a laundry list to get done. This is teaching your kids how to think. It's teaching them a lot of the skills they're going to need later in life, and also giving them a direction and a focus. And again, it's very interactive. We love to get feedback. The worksheets was based on feedback. We didn't used to have worksheets, but now we've got like 1,700 worksheets for the program. And so the careers are in there. Another one was science fair projects. A mom came in and said, "I'm ripping my hair out. My kid needs to do a science fair project, and I just learned about it. It's due tomorrow." Couldn't help her in the moment, but I thought about it. I'm like, what a great idea. So I created an entire science fair project area. You go under menu and you click on science fair projects. And now these are 8 of my very favorite science fair projects. And no kidding, the kids that actually follow step by step, whether they're doing the hovercraft, the linear accelerator, the rocketry, the underwater robot, the battery-free radios, whatever it is, they win prizes. We have a whole page just on all the images from people that have sent in like, "Oh, thank you so much. My kid won first prize," or "My kid won this. It was amazing." So the kids follow the steps and they're doing really well because we show them exactly what you need to do to think like a scientist, to communicate like a scientist. Everything's in there. Okay, so let's see. What else can I tell you about the site real quick? There's questions. So if you write in a question and you click on questions, you'll find the answers to the questions. Let me think what else. Oh, how to keep a science fair journal is also in here because that's really critical. I mean, your ideas are worth nothing if you can't communicate them with other people. So how do you keep a science fair journal? So I taught mechanical engineering at Cal Poly State for many years. And so I took the lab reports and the lab journals that we had the college students using, and I made those into, that's what you're going to find there, and how to keep a science journal. So this is actually what's being used in the university. Okay, and so that's in there as well. And there's also a math course. Now, this is not a full-blown comprehensive math course. This is how to keep your kids interested and excited in math, and how to really see it's the language of science. So this is, one of the questions we get is, how much math does my kid need to know in order to do your science? And the answer is none. I mean, as long as they know their multiplication tables. If they don't, then it makes it kind of hard. But as long as they know at least 4th, 5th, 6th grade level math typical 6th grade level math, then they're fine. We actually teach them the math alongside the science. So we're going to teach them about logarithms, we're going to teach them about vectors and trigonometry, the beginnings of calculus, all alongside, so you can see where it's used. Because otherwise it's just the stuff you learn and phew, out the window next month, right? I want them to actually understand how and when you're going to use them. And so that's when we do it. So when we actually get to physics, when we do rocketry, we talk about projectile motion, we start talking about squaring, we start talking about quadratic formulas, all of that's in there. So you don't have to memorize anything. You'll really get a good feel for how all of this stuff works together. Okay, I hope this has been helpful. If you have any questions, let me know. I'm Aurora at superchargedscience.com, and I look forward to seeing you next time at the next class that we're going to do. And it looks like we have a marine biology class coming up soon and a robotics class. So make sure you get on my email list. Just click on superchargedscience.com and then go to free stuff, and you'll get a personal invitation for my next classes when we're doing them. And I will see you folks next time. Thank you, everybody.